Dr. Bill Frez is a board-certified toxicologist with over 25 years of experience in the specialty chemical and consulting sector. His experience includes chemical residue analysis for fate and transport models, toxicology testing, and risk assessment support. He also consults with the chemical industry at all stages of development and use and provides insight on toxicity and alternative design options. Dr. Frez is an active advocate for existing and emerging chemistries and industry in consortia and also in industry trade groups. Dr. Frez received a PhD in Environmental Health Sciences from the University of Michigan, Master's in Biology from University of Michigan as well, and a BS in Biology from Wayne State University. So Dr. Frez, I would gather you're from Michigan.
I am, but currently living in Ohio. Again, appreciate folks taking the time out of your busy day to listen to some discussion about this important subject. I, along with our senior risk assessor at the EHS support, Dana McCue, will be tag teaming this presentation. I'll spend a little bit of time. Dana, we can go to the next slide, if you will. I'll spend a bit of time introducing PFAS. I think a lot of this information is information that you already understand. Maybe the context will be a little different. And I'll give you a brief overview of PFAS toxicology. We're not going to take a real deep dive into that. We have other experts on the panel that will provide more detail in that respect. And then I'll pass the baton, if you will, to Dana, who will build on the environmental sources and fate and transport and develop a conceptual framework for exposure to PFAS through food and beverage. We'll discuss some regulatory issues and then summarize accordingly. So let's give it a shot. As most of you know, the PFAS are an extremely complex class of chemicals, well over 5,000 individual substances that vary in their alkyl chain length, the degree of fluorination. They've been widely used for several decades, primarily for their grease and water resistance, and have been used in Teflon, firefighting foams. Particular interest to this presentation is food packaging and of course food products. Interestingly and somewhat distressingly, 6 million Americans are exposed to PFAS in drinking water in excess of some regulatory environmental levels. That includes EPA recommended levels as well as individual state levels that are being promulgated. Really based on the complex nature of the chemical class, grouping PFAS into sort of a behavioral, a similar behavioral group is highly complex. The fate and transport characteristics differ significantly depending upon the nature of the substance. But we do know that to some extent we have found residues in food products and of course in drinking water and potentially in beverages that may make use of impacted drinking water. We think that's not a particularly significant issue, but that's still something that awaits the science. With those potential exposures, of course, we're concerned that the PFAS have been shown to have some adverse physiological effects, and we'll discuss that in a little bit further on, and I'm sure others will as well. Next slide, please. This slide is sort of interesting. The graph on the top of the slide is a Google Trend search. Their Google Trend search statistics for PFAS in general. And the point that we'd like to make here is that shortly after the ATSDR issued its tox profile for PFAS in 2018, the number of hits on Google really increased dramatically and continues to do so, despite the fact that Pfas, as I said, had been used for many decades. So this is an area, as Wendland had suggested and Neil had mentioned, is one of great scientific and health concern. The bullets that you see below confirm that many states are interested as well, and that interest is increasing somewhat exponentially, I would think, over the next few years. So go to the next slide, please. This is a very broad brush presentation of the toxicology of PFAS. We're learning more on a daily basis, but we do have evidence that PFAS impact the endocrine system, impact thyroid function. There's some indication that cholesterol levels can be increased. Immunotoxicity has been a concern, as well as reproductive toxicity and unfortunately potential for low infant birth weight. I do want to point out that the National Toxicology Program recently, I want to say back May of this year, presented its findings on the carcinogenicity of perfluorooctanoic acid, and the conclusion was there's clear evidence that that particular PFAS chemical is a carcinogen in animals that were tested. Let's go to the next slide. In terms of sources, we can break down the environmental sources into two major categories. Primary sources, primary point sources, which, as you might know, are sources that are associated with industrial activities, fire training responses, landfills, waste treatment facilities that provide biosolids potentially for agricultural use, and then non-point sources, which really are the focus of our symposium today, potentially food packaging and food products, and then associated drinking water. Of course, there's a bevy of other sources that we can address, but suffice it to say, there are a number of potential sources that exist. Next slide, please. Having some understanding of those sources allows us to have a very somewhat broad conceptual framework for the environmental fate and transport of the material. This is somewhat of a busy slide, but I think it emphasizes that depending on the specific chemical nature of the substance, whether it's a long chain material, whether it's a short chain material, low molecular weight, transport processes can range from distribution to groundwater, runoff to surface water, long-range transport, potentially atmospheric deposition, all leading to exposures to agriculture and ultimately to the humans. And with that, I'm going to click off my camera and allow Dana to build on what's been said. I appreciate you folks listening to me. Thank you.
So Ms. Dana McCue is an environmental professional with over 30 years experience in human health risk assessment, site investigation, remediation, and environmental chemistry. As senior risk assessor at EHS Support, Dana performs assessments of contaminants such as chlorinated solvents, polynuclear aromatic hydrocarbons, heavy metals, and of course, PFAS. Ms. McCue received a master's in public health from Emory University and a BS in biochemistry from Florida State University. So Ms. McCue, I'll pass it back on to you.
All right, so in the prior slides that Bill just went over, he gave a brief overview of PFAS and potential point and non-point sources of PFAS and its environmental fate and transport. In the next few slides, we'll build upon that source pathway receptor paradigm by reviewing potential exposure pathways by which humans may be exposed to PFAS. Namely, for this presentation, we're focusing on food, food packaging, and beverages. Potential human exposure pathways for PFAS include inhalation, incidental soil and dust ingestion, dermal contact, diet, and drinking water ingestion. As indicated in this table on the slide of estimated relative source contributions of these potential pathways, there is a general agreement that dietary intake is the largest source of PFAS exposure, and that drinking water is the most important pathway for communities affected by point source releases that Bill identified. For an example, next to contaminated sites, drinking water has been reported to account for up to 75% of total PFAS exposures. However, most of the studies that are cited in this table and that we'll discuss throughout the presentation come from the European Union, and in the United States, we still need more data to fully understand the relative importance of different exposure pathways and whether the same pattern with regards to the importance of diet is also present in our country. So when we talk about food exposure pathways, first we need to understand how PFAS may end up in the food that we eat. The food exposure pathway is a work in progress, and some of that work will be discussed in more detail by our next speaker, but we will provide a preliminary understanding based on the latest science to help you understand where PFAS may enter the food supply chain. At a high level, there are two primary routes of PFAS into food, that being bioaccumulation at the source, and then exposure via processing and packaging. We can break down that high level of understanding a little bit further in this slide. This figure further details the bioaccumulation related pathways in the food chain, which is depicted by the blue outline boxes. And then the transfer pathways from contact food materials used in food processing and packaging, as depicted by the green outline boxes. It is considered that processing-related pathways reflect current production use of PFAS, while bioaccumulation-related pathways reflect long-term use of PFAS. So let's break this down even further, beginning with bioaccumulation and biosolids. One way that PFAS may enter the food chain is through the application of residuals such as biosolids, industrial sludges, and ashes. Biosolids contain nutrients and other organic matter that can enhance soils and agricultural production. Therefore, PFAS chemicals can end up in a wastewater treatment plant's waste stream sludge from everyday household activities as well as from industrial sources. Studies suggest that PFAS and biosolids, which is applied to farmland, can then be transported to adjacent surface water and underlying groundwater. And then PFAS crop uptake from biosolids contaminated agricultural soil may be a source of dietary exposure. At the federal level, current EPA biosolids regulations do not have limits set for PFAS. However, some states have established such regulations. For example, in the state of Maine, the application of residuals on agricultural land is permitted and regulated by the Maine DEP. They've also set limits for two PFAS chemicals, Pfos and PFOA, in biosolids. So in crops, there has been research conducted by Blaine et al. As well as many others that have shown that edible crops can uptake PFAS from impacted soil, including soils that are amended with biosolids as well as industrially impacted soil. Short chain PFAS in particular were shown to accumulate in the studies that are depicted on this slide, as well as studies that have been conducted by others, including in the state of Minnesota. Many factors do affect the bioaccumulation of PFAS into crops, including the crop type, the soil properties in which the crop is grown, as well as the source concentration of PFAS in soil or in impacted water. In comparison to the accumulation of short-chain PFAS in crops, in fish and beef, bioaccumulation potential is high for certain long-chain PFAS, in particular PFOS. Higher chain PFAS concentrations are typically seen in seafood as compared to beef. An important item to note is that compared to other persistent chemicals, PFAS partitions to protein rather than fat and lipids. Blood, liver, kidney, and muscle are primary repositories of PFAS. In addition, PFAS are generally not metabolized or metabolizes to persistent PFAS precursors. The presence of PFAS in other non-traditional food sources has also been assessed to a limited extent. For example, Michigan has done a study in deer. There have been studies done on loon eggs in the Northeast, in New Hampshire and Maine. Waterfowl has been studied in Australia. And then there was a Canadian study which indicated the presence of PFAS in caribou. As depicted earlier, PFAS in grease-resistant food packaging can leach into food and increase dietary exposure as well. It is considered that processing-related pathways reflect the current production and use of PFAS. For example, PFAS currently used in food packaging are mainly short-chain varieties and fluorotelomere-based derivatives. Studies have shown that the presence of PFAS in many types of food contact materials, as shown in the figure on the right-hand portion of the slide. In one such study, PFAS or fluorine-containing compounds was detected in food contact papers as well as paperboard samples. In this study, they used total fluorine as a surrogate to measure PFAS. So the high water solubility of PFAS, which Bill mentioned earlier, has led to the presence of PFAS in groundwater and surface water, and then the contamination of drinking water resources. PFAS contamination of drinking water was first reported in the United States in public and private drinking water supplies near a fluoropolymer manufacturing facility in Washington, West Virginia in 1999. Between 1999 and 2017, our understanding of the occurrence of PFAS has expanded greatly due in part to both statewide surveys of public water supplies as well as a nationwide survey conducted by EPA under the third unregulated contaminant monitoring rule. Results of these investigations and surveys have indicated that drinking water concentrations of PFOS and PFO in particular exceed US EPA's current 2016 health advisory level. And as Bill mentioned, this affects approximately 6 million Americans. The figure that is shown on this slide depicts the discovery, as I mentioned, discovery of sites contaminated by PFOS across the country between 1999 and 2017. This figure was adapted from data compiled by Northeastern University's Social Science and Environmental Health Research Institute and was last updated in late 2017. And the colors of the circle on this slide represent the different types of pollution sources, the different point sources that Bill had mentioned. And then the magnitudes of those circles indicate the size of the local communities that are impacted. And then the figure that's to the smaller figure to the right shows the current map as of July 2020 with different color dots showing drinking water supply sources that have PFAS detections, sources at military sites, as well as other sources throughout the country. So it is an ever expanding, changing map. So now that we've laid out how PFAS might move into food and beverages, let's discuss our current understanding of what we've measured in our diets. Most food supply data that we have reviewed has been collected in the European Union. In that study, results indicate the presence of PFAS across various food categories. The detections were most frequent in meat and fish, and consistent with prior discussions, high concentrations of PFAS in fish were followed by meat. In the United States, there were comparatively fewer detections in FDA testing of the general food supply. The sample sizes are limited in the FDA study as compared to that in the European Union and cannot be used to draw definitive conclusions. However, based on the best available current science, there is no indication that PFAS at the levels found in the limited sampling present a human health concern. And then our next slide kind of goes into a case study of a statewide survey that was done by the state of Maine to evaluate the occurrence of PFAS in milk. The state of Maine conducted a statewide retail milk survey to assess the safety of their current milk supply. After 2 rounds of sampling, they determined there was a high confidence in the safety of Maine-produced milk. During the sampling, Pfos was detected in one retail milk sample. However, the source of the detection was then traced back to a commercial dairy farm, and that farm is no longer contributing to the milk supply. Importantly, as part of the study, Maine established an action level for PFAS in milk. This level provides guidance to determine when cow's milk is considered adulterated and therefore can be removed from the market. And so this is the only action level that has been established so far. So we know that PFAS is widely distributed in the environment, and we have a sense for how humans may be exposed to it. But so the next few slides, we're going to look at the current state of regulations regarding PFAS. With the exception of the action level in Maine that we just discussed, the sparsity of data in the US hasn't allowed for risk assessment and development of food standards or acceptable food safety levels. As a result, the current regulatory inroads into food have been through food packaging in particular. Regulations at the federal level that address food packaging include the Food, Drug, and Cosmetic Act and the Food Contact Notification Program. FDA has banned PFOA and PFOS in food packaging and most recently announced a phase out of the 6,2-fluorotelomere alcohol. At the state level, several states, which are depicted on this figure on the right, have adopted or have proposed bills banning or limiting PFAS in food packaging as well. Because the highest concentrations are found in drinking water, as we previously discussed, in the vicinity of point releases, there's been a focus on regulating drinking water at both the federal and state level. As we mentioned earlier, in 2016, EPA set a lifetime health advisory for PFOA and PFOS. There are currently no enforceable MCLs established for PFAS chemicals, but EPA has started the process looking into establishing those MCLs. The states, however, have been more proactive in establishing regulatory criteria, which is shown in the schematic in the middle of the slide. However, at the state level, there is a lack of consensus in the toxicity data used to establish these levels. Therefore, the standards at the state level vary by orders of magnitude. In addition, at the state level, various states have also been expanding their statewide testing of public drinking water supplies and publishing those findings for the public on their websites. Some states also, most notably in the Northeast, are also providing the public with bottled water testing results. So what is our path forward for understanding PFAS? There are data gaps that need to be filled to fully assess risk posed by the diet to Americans, namely concentrations in food and the pathways through which PFAS end up in food. To fill these data gaps, there are certain research initiatives that are being undertaken at the federal level, as well as other testing programs in some states. For example, PFAS was recently added to USDA's Food Safety Inspection Service testing and meat processing plants, which will be discussed in the following presentations. There's also been additional funding for research on PFAS in agriculture. FDA is continuing their total diet survey PFAS testing. And as we briefly touched on at the state level, there's been testing of food products such as milk, and then biosolids are used in the agricultural industry. So in summary of the slides that we presented, as we've discussed, PFAS are a human health concern, and the diet is the primary human exposure pathway. PFAS may enter the food supply either via the processing plant, via bioaccumulation from environmental sources. With the exception of drinking water, the risk posed by dietary exposure has not been fully defined. We have identified some data gaps. In addition, regulations have also been focused on drinking water and food packaging, but there have not been food standards established to date. However, agencies are increasing their research focus on PFAS in food and agriculture.